We're surrounded by these incredible invisible forces all the time. They're strong enough to hold back a whole lake. They're the reason you can smell cookies baking from another room. And believe it or not, they're pushing on you from every direction right this second. So today, we're going to pull back the curtain on two of the biggest ones, pressure and diffusion.
All right, let's kick things off with a little mystery. You've definitely seen pictures of these massive dams, right? But have you ever stopped and wondered why they're all built in that same kind of strange triangular shape?
I mean, if you look at one from the side, the top is pretty thin, but the bottom is incredibly thick and wide. And that's no accident. It's a super clever piece of engineering that's based on a really fundamental idea in physics. So what's the deal here?
To solve our dam mystery, we first have to talk about the weight of water. Now, a single glass of it doesn't feel heavy at all. But when you get an entire lake's worth of water all stacked up, well, that weight adds up to an absolutely immense force.
And that immense force is what we call liquid pressure. It's basically just gravity pulling down on every single water particle. But, and this is the really key part, unlike a solid brick that just pushes down, liquid pressure pushes out equally in all directions at once. Sideways, down, up, you name it.
What's really crucial to understand is that this pressure isn't the same everywhere. Right near the surface, there's only a little bit of water above you pushing down. But as you go deeper and deeper, the weight of all that water above you just builds and builds. By the time you get to the bottom, you've got the entire weight of the lake pressing in on you.
And boom! There's the answer to our dam puzzle. It all makes sense now. The dam has to be massively thick at the bottom because that's where the water pressure is the absolute strongest. It's literally fighting against the weight of the entire lake. This is the exact same reason submarines have to be built like armored tanks to survive that crushing intense pressure of the deep ocean.
Now, this idea doesn't just apply to water. It's really easy to forget this, but all of us are living at the bottom of a vast ocean of air. And just like the water in a lake, all of that air has weight, and it creates its own powerful pressure.
Gas pressure works a little differently, though. It's caused by trillions and trillions of tiny, invisible particles moving around at super high speeds. Just imagine them like microscopic bumper cars, constantly buzzing around and crashing into everything in their path. Each little bump is a tiny push, but when you get trillions of them happening every single second, they create a steady, powerful force. So what happens when we add heat into the mix? Well, heating up a gas gives its particles a ton more energy. They start zooming around way faster, which means they collide harder and more often. All that extra action ramps up the pressure. It's why a bike tire can feel rock solid on a hot summer day. And of course, the opposite happens when it's cold. The particles slow down and the pressure drops.
Okay, this brings us to a really cool thought experiment. Right now, if you think about an empty soda can, you've got air particles on the outside pushing in and air particles on the inside pushing out. It's all in perfect balance. But what would happen if you could just snap your fingers and magically remove all the particles from the inside?
Well, the result is instant and pretty dramatic. With nothing pushing back from the inside, that immense pressure from the atmosphere on the outside wins, and it's not even a fair fight. The can is immediately crushed flat by that invisible force. It's a powerful reminder of the pressure that's all around us, all the time.
So we've seen how these particles create pressure by colliding with things. But all that constant movement leads to another really cool phenomenon. I mean, think about it. How does the smell of fresh popcorn from the kitchen make its way all the way to you on the couch? Those scent particles literally travel through the air all by themselves.
That process is called diffusion. It's simply the natural, random movement of particles from an area where there are a lot of them, what we call a high concentration, to an area where there are fewer of them. It's just a fundamental way that things mix together in our world, with absolutely no stirring required.
A great way to picture this is with a drop of food coloring in a glass of water. At first, you have that single, super concentrated drop of ink, but because particles are always in random motion, they just start to spread out into the water. They keep moving and mixing and bumping around until they're all evenly distributed, and that's when the whole glass of water is one color, a state we call equilibrium.
And you see diffusion constantly. That smell of dinner, that's just food particles diffusing through the air. When you make a cup of tea, you are literally watching tea particles diffuse from the bag into the hot water. It is a process that is happening all around us all of the time.
Okay, so we've got a pretty good feel for pressure now, but to really understand how it works in all these situations, from dams to soda cans, we just need one simple tool, a formula that ties it all together.
And here it is. It's super simple. Pressure equals force divided by area. This little equation shows us the two things that really matter: how much force you're applying and the size of the area you're applying it over. This is where that formula really comes to life. Let's take the same force, a person's weight. If you apply that force through the tiny point of a stiletto heel, the pressure is absolutely massive. But if you spread that exact same force over the large area of a snowshoe, the pressure becomes so low that you can walk right on top of snow without sinking.
So the big takeaway here is that the area is just as important as the force. A sharp knife can slice a tomato because it concentrates all your force onto a microscopically small area, creating huge pressure. A dull knife spreads that same force out over a wider area, and, well, you just end up with a squished tomato.
So whether it's the shape of a giant dam or the sharpness of a knife, these big ideas of pressure and diffusion are constantly at work, all driven by the simple push and spread of tiny, invisible particles. Which kind of leads to one last thought. If tiny things can create such huge forces, what other invisible forces might be shaping the world around you right now?